Welcome to The Explainer. Today, we're diving deep into the nitty-gritty of electronics, and it all kicks off with a really simple question.
You flip a switch and things just work, right? Well, today, we're going to pull back the curtain on the split-second drama that unfolds inside a circuit the very instant you power it on. It's this moment of incredibly rapid and, honestly, super fascinating change. We're going to investigate three fundamental circuits: the RC, the RL, and the LC. We want to see how they react to a DC voltage source the moment that switch closes. We're talking at time t=0. This brief, kind of chaotic period of adjustment is called the transient state, and it happens right before the circuit settles down into its stable, predictable, steady state. That first moment, t=0, that's our focus. That's when all the action begins.
All right, first up is our first character, the RC circuit. You can think of this one as the charger. Its story is all about a slow, methodical charging process, kind of like filling a bucket with water, one drop at a time.
So this circuit has just two main parts: a resistor, R, and a capacitor, C. Now, a capacitor is all about storing energy in an electric field. Think of it like a tiny rechargeable battery. So when we close that switch, charge starts to build up. And the big question we're asking is, how do the voltage across that capacitor and the current in the circuit behave over time while this is happening?
And check this out. As soon as the switch closes, current rushes in. But as the capacitor starts to charge up, the voltage across it builds, and that voltage actually pushes back against the source. You can see it perfectly in the graph. The voltage climbs up, while the current, it just fades away exponentially. It's this beautiful inverse relationship. As one goes up, the other goes down. A perfect trade-off.
So how fast does this all happen? Well, that's defined by something called the time constant, represented by the Greek letter tau. It's super simple, just R times C. The bigger the resistor or the capacitor, the bigger tau is, and the longer the whole process takes. The math is pretty elegant, really. You get one decaying exponential curve for the current and an exponential rise to the final voltage for the capacitor.
But here's the really crucial part to remember. At that exact moment the switch closes, at t=0, an uncharged capacitor acts just like a short circuit. It offers basically zero opposition. It's like an open floodgate, allowing the maximum possible current to just rush right through.
Okay, moving on to our second character, the RL circuit. We'll call this one the momentum builder. If the RC circuit was like filling a reservoir, this one is all about building up momentum. Kind of like a heavy freight train slowly getting up to speed.
So here, we swap out the capacitor for an inductor, L. An inductor stores energy too, but it does it in a magnetic field. And its defining personality trait? It hates change. It will fiercely oppose any attempt to change the current flowing through it. So, what do you think happens when we slam that switch shut and try to force current through it instantly? Well, unlike the capacitor, the inductor initially blocks all current. It's like, nope, not happening. But as its magnetic field slowly builds up, it gradually gives in, allowing the current to rise until it eventually just acts like a simple piece of wire. This is a brilliant illustration of that. The inductor's opposition, its back EMF, just fades away over time.
And the math here, it's governed by a new time constant, tau, which is now L divided by R. But wait a second, do these equations look kind of familiar? They should. They're almost a mirror image of what we saw with the RC circuit.
This is a really cool principle in electronics called duality. Check it out. The formula for the inductor's current is a dead ringer for the capacitor's voltage. And the inductor's voltage formula, it matches the capacitor's current formula. It's like they're mathematical twins, just playing opposite roles.
So at that very first instant, the inductor acts like a completely open circuit. It generates a voltage that's equal and opposite to the source, totally blocking that initial flow of current. It's a complete flip from the capacitor. The capacitor welcomed the current, but the inductor at t=0 fights it with everything it has.
All right, on to our final character, the LC circuit. I like to call this one the oscillator. Now, what happens when energy has absolutely nowhere to escape? This is where things get really, really cool.
See, with this circuit, there's no resistor. And the resistor is what dissipates energy as heat. So without it, the inductor and capacitor just continuously exchange energy. It goes from the capacitor's electric field over to the inductor's magnetic field and then right back again. It creates this perfect, sustained oscillation. Imagine a pendulum swinging back and forth forever with zero friction.
And forget those exponential curves we saw before. In an ideal LC circuit, the voltage and current are these perfect sine waves, just forever trading energy. You can see it here. The capacitor charges up, then it discharges into the inductor's field builds up, then collapses, which then recharges the capacitor, and the whole cycle just repeats over and over.
This endless exchange is all described by sinusoidal functions. And its speed, that's determined by what we call the natural resonant frequency, which only depends on L and C. The huge takeaway here is that this circuit resonates. It creates a pure, oscillating tone. This isn't just some abstract idea, by the way. This is the magic behind tuning your radio. So there you have it. 3 circuits, 3 totally different personalities. Let's bring our transient trio back on stage for one last look.
This table does a fantastic job of summing it all up. You can see their unique signatures right here. You've got the exponential charging for the RC, the exponential energizing for the RL, and that beautiful sinusoidal oscillation for the LC. Each one tells its own story.
And here you can see the whole story in one single view. You've got the charger, the momentum builder, and the oscillator. From how they behave initially, like a short or an open circuit, all the way to their final steady state, each one tells a really fundamental story about how energy works. So the next time you flip a switch, you can ask yourself, which one of these stories is unfolding inside? Thanks for joining this explainer. Now you know what really happens in that first moment of truth.